Okay, I think we can start. And I see there's already one Q&A question in the Q&A session. So later maybe Prof Yo will answer this question after he's sharing. So now we can move on to our tutorial.
Okay.
Sure. Let me introduce Prof Yo to everyone. So Prof Yu is a Presidential Young Professor at the NUS, and he received his PhD in computer science from UC Berkeley. And Prof Yu's research interests include the parallel or distributed algorithms, high-performance computing, and machine learning. And he's also the winner of IPDPS 2015 Best Paper Award, and also that of 2018, and also an ACM IEEE George Michael HPC Fellowship, and so on. So now I will handle my time to Prof Yo for his sharing and tutorial. Prof Yo.
Okay. Thank you, Injie. Okay. So can you see my slides?
Yes, we can see it.
Okay. Good. Thank you. Okay, folks. I'm very happy to be here. So today, let me introduce better system or new system for distributed AI, which means we hope we can build a new system to make the large-scale AI training easier. So the name of our system is Colossal-AI. So we actually already opened the source code on GitHub. So if you like, please check the GitHub code and also the tutorial. Please let me know if you have any questions. Okay. So I'm going to skip this page because Injie already introduced me. By the way, so my research interests include high-performance computing, deep learning optimization, or for example, the optimizers, and also machine learning system. So without further ado, let's go to today's talk. For today's talk, so I have 5 parts. So in the first part, let me give you a brief background and overview. And later, I introduce the key techniques and also the results. And eventually, I will give you a summary. Okay. For the background, let me show you a figure. So for this figure, the horizontal axis is a timeline by year. For example, year 2013, year 2015, year 2017. The vertical axis is the floating point operations or the computational cost of our state-of-art AI models. So here the unit is a million, 10 to the power of 4 million. It means, so from here you can see, we know roughly in year 2017 the best model is AlexNet. However, today we have some very powerful model like AlphaGo or GPT-3 or PML. So they are much more computationally expensive. So according to OpenAI, the computational cost of our leading AI models actually can increase 35 times for every 18 months. However, we know even we have more through, the computational power of our chip only increase roughly 2 times for every 18 months. So there is a huge gap between demand and supply. That's a big concern, and this gap is becoming larger and larger in the next few years. Okay. Let me show you a second figure. So the horizontal axis is also the timeline by year 2017, year 2018, 2019, 2021. The vertical axis is the number of parameters in the AI models, or the size of AI models, or the memory requirement of the AI models. We know in 2017, in 2016, the best AI model is probably less than 50. So today we have something like a GPT-3 or OPT or Facebook's OPT. So according to OpenAI, still the size or the number of parameters of our leading AI models, they increase roughly 40 times for every 18 months. And if we count from 2019 to today, so they increased roughly 340 times for every 18 months. That's very crazy, I think. Because we know the memory on our single chip or single GPU, the memory size only increased roughly 1.7 times for every 18 months. So there is a growing gap between demand and supply. We know in the next probably next 10 years, quantum computers probably not ready yet. So we think in the next 10 years, we need to use still the current computer architecture to do AI training and inference, because quantum computers probably not ready. So the only solution for the current computer architecture, I believe, is parallel and distributed AI. That's the only practical solution so far, I think. So, however, we know distributed AI is not easy, it's not efficient, and there are several different reasons. The first reason we know now today we have lots of unlabeled data, like Facebook users, they can upload more than 1 billion users per day. YouTube users, they can upload hundreds of like 500 hour videos per minute. And also we know the cost of labeling the data set is very high. So which means the speed of generating the data is much higher than the speed of labeling, carefully labeling the data. That's why we have lots of unlabeled data set. So, but however, if we want to do data mining, to make full use of the unlabeled data sets, so that's why we need a very large model or complicated model. We need a pre-training transfer learning. That's why our model is becoming larger and larger. And also, we know we have many computer architectures and AI training frameworks, like CPU, GPU, TPU, or ML frameworks like TensorFlow, Keras, PyTorch, pathways. All these three factors, they are making distributed AI more complicated and and make distributed AI inefficient. That's why we want to build a new system, Colossal-AI. Later, I will introduce more about Colossal-AI. So the motivation is, by using Colossal-AI, we hope we can make training large AI models easier, especially in the future. We hope the users, they just need to write a few lines of code on their laptop, and our Colossal-AI can automatically help them to deploy their code to cloud and supercomputers. So let me also briefly review the existing solution, because now it's a kind of hot topic. There are also some solutions from industry. For example, NVIDIA, Megatron, Microsoft, DeepSpeed, Google's TensorFlow, G-Type, G-Shard, Facebook's Fast Scale. Let me briefly give you a background. And later, let me introduce why Colossal-AI is unique. So again, for Colossal-AI, we hope we can build an abstract layer, so the users just need to write the code based on TensorFlow, PyTorch, and we can, the user just need to write the code on their laptop. We can help the user automatically to deploy their laptop to cloud and supercomputer and help them to get the best performance on CPU, GPU, NPU, or any architectures, or any cloud platforms. So now let me briefly introduce. So what's the key techniques of Colossal AI? The first key technique is we know we need to get enough parallelism because we need to handle hundreds of GPUs or even thousands of GPUs. To do that, we need enough parallelism. Otherwise, the utilization rate of our hardware will be very low. So now the question is, so where the parallelism come from? So how can we get enough parallelism? Currently, so the main parallel computing techniques for AI is data parallelism, pipeline parallelism, and tensor parallelism. So for data parallelism, it's very easy, and also it's the most widely used approach. We just need to partition the data to different processors, and each processor can compute its own gradients, and then we do an overreduce operation. Then we have an overreduce operation to get average of gradients, and the average of the gradients is the global gradient, and then we broadcast the global gradient to all the nodes, and each node can use the global gradient to update its local weight. That data parallelism. So the pipeline parallelism is kind of very very useful for today. So basically, we want to build different pipes. For each pipe, we also partitions the mini batch into different micro batch. So different pipes they will have different different data. So that's why they can compute X at the same time concurrently, because they are essentially using different data for different pipes with pipeline parallelism, and also tensor parallelism. So for tensor parallelism, we partition the tensor to different devices, and we finish the computation of one tensor one layer, and then we move to the next layer. That tensor parallelism. So the most widely used approach for today is Magtron, NVIDIA Magtron, and also Microsoft's DeepSpeed. So the key idea of Magtron is 1D tensor parallelism. So the key idea of DeepSpeed is zero and offload. So there's the current solutions. So however, what can we do to improve the current solutions? So for us, and we want to build all the parallelism together, and also we want to build a unified interface. Firstly, we want to have all kinds of parallelism. So we have 1D pipeline data parallelism, and also we propose some new approach like 2D, 3D, 2.5D tensor parallelism, because we believe they can make the future huge AI models more efficient, because we have much more parameters. The 2D, 3D, 2.5D, we hope to make them more communication efficient. That's why we do that. And also we propose a new parallelism, sequence parallelism for the future applications like 5G metaverse. We will have lots of long sequence data. That's why we want to design the sequence parallelism. And together, we want to build a unified interface. By unified interface, we want to minimize the efforts of the users. The user just need to use a unified interface to automatically enjoy all the benefits of the different parallel computing techniques. That's what we are doing. Now let me briefly go over the techniques, and then I introduce the tensor. So we know for Magtron they use 1D tensor parallelism. However, for 1D approach, they need to all reduce or gather. So this or reduce or gather operations, they needed to make each machines to talk to all the other machines. So that's communication very intensive. So for us, for here, we want to do the 2D tensor parallelism approach. We partition the tensor into a grid. So which means we want each machine just need to communicate with the same row or same column. For example, 1D approach, we have 10,000 machines, and each machine need to communicate with 9,999 machines. For here, 10,000 means 100 by 100. So so 2D approach, each machine only needs to communicate with 99 machines, which means we hope we can reduce the communication overhead significantly. And also the same idea for 3D. For example, we have 1,000 machines. For the 1D approach, each machine needs to communicate with 999 machines. For here, we want to make 1,000 partitioned into 10 by 10 by 10. So each machine only needs to communicate with 9 machines. That's the idea of 2D and 3D, and also 2.5D. We make a different copies of 2Ds. That's the rough idea for the higher order tensor parallelism. By doing so, I think we have better performance. Why? So let me give you a brief comparison. Here is a comparison: 1D approach, 1D tensor parallelism, 2D, 2.5D, and 3D. So for the computational, they are the same. And for the memory cost, for first memory cost different parameters. For 1D, it's 1 over P. Because for 2.5D, we make multiple copies. It's D over P. And for 2D and 3D, they are also 1 over P. However, for activations, I think we can significantly reduce costs of activation for 1D because it's kind of constant for us, and it's 1 over P, 1 over P, 1 over P, which means we have more machines. We can significantly reduce the memory costs, and also communication costs for bandwidth. 3D is much better, and also for the latency cost, 3D also much better. That's the rough idea for tensor parallelism. So when you have more machines or more nodes, eventually 3D will become the best. And also we introduce sequence parallelism. So for sequence parallelism, so here the idea is in the future, for example, in the 5G applications or in IoT applications, you will have a long sequence. Now, for example, the recent AI model like VIT, even you want to process an image, you partition the image to different patches. So the number of patches actually is the sequence length. If you can imagine, in the future, you have some huge, very large images. Those images, they are so large, so you need to partition them to many patches. So sequence will be very long. And also, for example, some other applications like protein folding or DNA, so the sequence is also very long. So for the long sequence data, so even a single data point, a single sequence can cause an auto memory issue. That's why we want to have a new approach to also partition the sequence. We know for AI training, so the memory costs, memory consumption come from weights, gradients, and amino states, and also input data and activation. For example, your model is 1 GB. The the width IP32, the width will cost 4 GB. Gradients and for 4 GB. If you use atom or measures, it's 8 GB. In total, for this part, it will 16 GB. And also you have activation. So that's why we also need to partition the input data. It's very necessary in the future, especially your model is huge and also your sequence is very long. However, what's the concern here if you partition the sequence? Let me use a transformer as an example. For transformer, we know we have two major parts. The first part is MLP, second part is the attention. For MLP, it doesn't matter because they are after you do the partition, they are independent. You do not need to communicate. You do not need to do the communication. However, we know if we want to compute the attention score, each device will needs all the subsequence on all the other devices. That's actually very bad, because for the naive approach, essentially each device or each GPU needs to communicate with all the other GPUs. The communication overhead is very high. It's for example, we have P GPUs. The communication overhead is order of P square. It's terrible. But how can we solve this problem? Do we have a better solution? So inspired by RIN or reduce, we propose the RIN self-attention approach. What's the idea here? So let me give you an example. For example, S is a sequence. We partition the sequence to different GPUs. And now for each step, and we can get our own Q query or key, our query and the key on our own GPU device, and we want our query and the key to the computer get the first attention score. For the next step, how can we get a new key? Because eventually we will need all the other keys from all the other devices. So for the next step, how about that? We give our key to our right-hand side neighbor, and we get the new key from our left-hand side neighbor. And then we compute the second attention score. And we do the same thing in all steps and get a new key from our left-hand side neighbor and send our old key to our right-hand side neighbor. And also get a new key from our left-hand side neighbor and send our old key to our right-hand side neighbor. By doing so, we can get all the compute all the attention scores. If you remember that we have P GPUs or P devices, in total we need a P-1 steps. So that's how we can reduce communication overhead from order of P squared to order of P-1. That's our approach for sequence parallelism. So by doing so, we can significantly reduce the memory overhead. Let me show you a table. For here, so P is the tensor or sequence parallelism, B is the base size, S is the sequence length, M is the memory cost, T is throughput, which means is how many tokens can we process per second, higher is better. OM, out of memory. So for tensor parallelism, you can see, so it has much lower memory cost. Let me give you an apple-to-apple comparison. So let's only use tensor parallelism. Sorry, I probably said something wrong. So tensor parallelism has a high memory cost. So let me give you an apple-to-apple comparison. So we only use 1D tensor parallelism, and we only use sequence parallelism. Firstly, we fix the sequence length, and we linearly increase the base size with the number of GPUs. From here, you can see the memory cost of a sequence parallelism is much lower. And also the second solution is we fix base size, we linear increases sequence length. Clearly, you can see our memory cost is also much lower. And now let me give you a two-point comparison between our approach to sequence parallelism and Megatron. Clearly, you can see by using the same number of GPUs, we can use larger base size, which means we can make the workload per iteration larger, and also the tokens per second with the same number of GPUs, our speed is higher. Okay, which means we can use 7 times larger base size and also get 1 times speed up. And also let me also introduce the data parallelism approach for Colossal-AI. For Colossal-AI, we introduced many state-of-the-art approach for data parallelism like LARS. Because for data parallelism, our target is to maximize the batch size and also fix the number of epochs. That means if we fix number of epochs, we linearly increase base size, we are linearly reduce the number of iterations. So here the question is, can we converge to the same flat minimum? Because we don't want to converge sharp minimum. For sharp minimum, even we can get a good training accuracy, our testing accuracy is also very low. That's why naive approach, we increase the base size, but we will lose accuracy even we train the same number of epochs. Okay, so previously for me, I proposed a large and lamb algorithm. Basically, we have a very good implementation for large and lamb in the Colossal-AI. By using large and lamb, now we can increase the base size from, for example, for image training by resident Ripley, we increase base size from 250 to 32K and get the same accuracy in the same number of epochs. So that means we increase the base size by 8 times. We can reduce the number of iterations, here horizontal axis number of iterations by 8 times. That's why we can significantly speed up the training process. So here is the result for VIT range transformer. Clearly, you can see we increase base size linearly with the GPUs. The horizontal axis is the GPU number of GPUs, vertical axis is speed. And I think we get a very good scaling efficiency. By doing that, we can reduce the training time from 73 hours to roughly 30 minutes. And also for LARS and LAM, we can reduce the bar training time from 3 days to 76 minutes because we can reduce the number of iterations from 1 million to roughly 8,000. Okay, so I feel like you can check a paper with code on the application of LARS and LAM. According to paper with code, LARS and LAM are only library training algorithm. I feel like you can check. Okay. Okay, I finished the second part. So here application of LARS and LAM. I just want to give you a summary. Colossal-AI has a very good implementation, will help you to maximize base size without losing accuracy. Give you the best speed of data parallelism. Also, according to NVIDIA public GitHub, so LAM is 70 times faster than previous methods. Okay. Next part, let me introduce the memory system for Colossal-AI. So for here, firstly, we use the zero techniques by Microsoft. We have a very good implementation, and also we have the offload techniques. So if the GPU memory is not, we offload to CPU. If CPU not enough, we offload to NVMe. And also we have the 1D to 2D approach. Also, they can partition the activation. Furthermore, can reduce the memory cost. Together, we can build a very efficient memory system. And finally, let me give you an overview of Colossal-AI. As I mentioned in the beginning, we hope in the future, the users just need to write a few lines of code on their laptop, and we can build an abstract layer, which means that can be a black box for AI users. AI users, they do not need to worry about parallel distributed memory, memory efficient or energy consumption. We can automatically help them to deploy their code to cloud and supercomputer, give them the the best performance, and give them a very low memory cost and a very low energy cost. That's what we are doing. Okay. So for Colossal-AI, and we have many features to support our future target. And firstly, we have enough. We have all the parallelism, and also we want to separate the distributed implementation from model building, and also we want to make a different module independent and decoupled. We also want the user easily to integrate with other new features and other frameworks. Okay, so here is the system architecture for Colossal-AI. Essentially, we want to build a unified interface so that the users can just use one interface to have all the techniques. Okay, so now Colossal-AI is supporting PyTorch. For PyTorch user, you just need to change a few lines of code, and then we can use Colossal-AI to deploy your code to cluster. So here are the other results. For example, for GPU3, without the Colossal-AI, for example, you use Magnetron, you need 128 GPUs to train. For Colossal-AI, you only need 64 GPUs. And also, Colossal-AI can give you much lower memory cost, even for the the model not so large, like GPT-2, and also give you a very good speed. For example, for the model like GPT-2. So here, horizontal access, the number of GPU, vertical access is the throughput. Colossal-AI can give you a higher speed. And also for vision transformer, you see Colossal-AI can allow you to have large base size and also have a high speed. And also here, also comparison between Colossal-AI and the Magnetron. Okay, I finished. If you like, you can check our code on our GitHub, and also we have a tutorial. Okay, please let me know if you have any questions. Thank you.
Thank you, Prof Yo. I already see one question in the Q&A saying that, hi, Prof Yo, how do you view the current trend of federated learning?
Okay, yeah. So I think federated learning is a very important topic. Basically, the idea is want to protect your privacy, your data privacy in the future, right? And eventually, I hope all the users can keep their own data confidential. That's why federated learning is very important. So but how can we achieve that? I think we need to build a much more scale async algorithm for today. For now, we do the BERT training and machine training. We are still using sync approach, but I think for federated learning async is very necessary. So speaking of async, we need to have a much scalable optimization algorithm. That's too many challenges, I think. Very interesting, but.
Yes, I see. Yeah. And another question is, hi Prof, in the future, if different models are invented, may not be based on transformers, then what's the challenge to our colossal AI?
Okay, yeah, no problem. So I think Colossal-AI is a very general system, not just for transformers, and also can work with can even work with seeing other future tensor-based model. But I believe no matter how they change the model, they will be based on tensor, right? Or tensor or matrix. And the Colossal-AI should work with any tensor-based or matrix-based models.
Okay, sure. Thank you, Prof. Yo. And for the friends, if you have any other questions, then you can just post in the Q&A section or just type it out in the chat.
Okay.
But I think we still have more time, so we can wait for a few more minutes for more questions if they have.
Okay.
Yeah. Oh, I received another one. What's the intended users of the system? How can individuals without luxury access to many GPUs benefit from it?
Okay. Yeah. Well, very good question. Actually, I believe all the users can use Colossal-AI. I think in next week we are going to release some new features. Because even the common users, they just have a server. They just have one laptop or desktop. For example, only one GPU. We hope, for example, without the Colossal-AI, they can just train, for example, 25 million parameters. We hope by using Colossal-AI, they can train 100 million parameters or even 1 billion parameters. That means even on some low-end hardware, we hope Colossal-AI can help them to improve the efficiency. I believe even without high-end hardware, Colossal-AI can helpful. We are going to release some features next week. Yeah.
Okay, thank you, Prof. Yo. And another one coming in saying, in the sequence parallelism part, what is the metric attention score means?
Yeah. Okay. Yeah. I think that's a background question. Probably, please check the transformer. Because for the transformer, we need to compute the cell of attention, right? So for cell of attention, it kind of you need attention score.
Yes. Yeah. So for this one, you can check on transformer later.
Okay.
And another question coming in saying, how will distributed learning paradigm promotes the reform of hardware, maybe GPU or ASIC or FPGA?
Okay. Yeah. Very good question. So we know for now, GPU. I think GPUs, they are dominating the distributed training market for AI. But for the ASIC, Google GPU, they are also very powerful. But it's kind of only on Google Cloud. And for FPGA, I think it's still for only most likely for inference. I think today, and also the compiling time of FPGA is too long. So that's the current situation for the hardware. Yeah.
Okay, thank you, Prof. Yo.
Yeah.
And friends, if you have any other questions, you can type in the Q&A or in the chat. Another one coming in saying, I can see Colossal-AI requires a lot of hardware, software co-optimization, and how does the recent release of NVIDIA GPU kernels affect or benefit from this?
Okay, yeah. So probably no major impact. That's because for us now, we want to build something above the CUDA layer. So if they can make sure they are well optimized, we can just take advantage of that. Yeah.
Okay, thank you, Prof. We still have a few more minutes, so feel free to type in any questions, friends.
Okay, India, so I have no questions. So shall we stop here?
Okay, sure.
Okay.
Yeah,
Okay.
so thank you, Prof, for coming, and
Yeah.
also thank you, friends, for all the questions.
Okay.
So our tutorial will end here. Yeah, thank you,
Okay.
Prof.
Thank you so much. Bye bye.